cool. Oh my God, that's my name. They made that for me. Hi, I can't see any of you because this light is in my eyes, but I'm sure there's at least 3 people here. Nice to see you. My name is Tejas. That's pronounced like contagious. I'm not contagious. It helps people pronounce my name. And I've had a really great tech career so far. I'm super thankful for it. I've worked with some of the best companies and teams ever, and I genuinely enjoy these people, and they're really nice. Today, I run a small business that helps developer-focused companies with DevRel, that's developer relations, because it turns out we're really bad at communicating as engineers. So we sell that to other companies. But that's not what we're here to talk about today. In fact, today I'm just here to do exactly that, to talk to you about event sourcing. I think it's important that I give you some context about this because I think it's important to know where the talk comes from. Okay? And it comes from this. I was at a conference. I tend to go to many conferences and speak at a lot of them. This is like 30-something this year of mine. And I was at a different conference one time, and there was a person talking to another person about event sourcing. Events, snapshots, CQRS, Kafka, this and that. And the person on the receiving end of this message, I could tell that they were a little bit intimidated. They didn't know what the person was talking about. And they were like, yes, no, that sounds cool, totally. And I was asking myself, why do people do that? And unfortunately, people do that because there's this like expectation to know everything. In engineering, there's this expectation to be smart, or smart, whatever. Like smart means something entirely different, right? But there's this expectation, oh, you haven't heard about event sourcing? You haven't heard about event sourcing? Come on. And so today, we're going to talk about it in depth. Literally, this was the motivation to create this talk. This is a 45-minute presentation, but it exists in long form. It's a 1.5-hour lecture. You can find that on the podcast that I've not yet started, but whatever, that'll come. Imagine watching people interact and looking at imposter syndrome and going like, oh my gosh, I need to make an 1.5-hour lecture, right? And so I did. And this talk is the subset of that. It's really the cliff notes, the important points, okay? How many of you use event sourcing in production? Okay, good. Why are you here? It's like, you don't have imposter syndrome. We'll talk, maybe you learned something. Tell me if you learned something after. But today we'll talk about what event sourcing is, why you use it, and some of the trade-offs, benefits, costs, things that get expensive, how do you optimize for them, et cetera, et cetera. We have a long time, so we'll make the most of it. Before we get into what it is, I want to show you, I can tell you and I will tell you, but I will show you first. Because when you have a bunch of events about things that happen, you can do some really great things. So you may have seen a logo on my introduction slide. I work with a number of different teams, in various capacities. And one of them is a company called CRUD Nebula, and with them, we're doing some really great work. And really, it's an event source system we're building together. And I want to show you that system so you can fully appreciate what happens, okay? CRUD Nebula they're a company that does stuff with Rust, as far as I know. They do security audits and they have a really cool website. This is the website, look at that. They made this. They have a design team that makes stuff anyway, so what do? Anyone use Tauri here? Tauri? Nobody. Okay, so Tauri is like Electron, but faster and smaller because there's no browser. It's just like a native OS web view and some Rust that binds the OS to the JavaScript. So your front end is JavaScript, your back end is Rust. Super light, secure anyway. So they're the company behind Tauri, which is a fully open source project. And so what they wanted to do was build this DevTools but for Tauri apps, like Chrome DevTools, but for Tauri apps. And Electron apps, anyone use Electron? Yes? Okay, like 3 of you. Electron is a way to build desktop apps with JavaScript. And Electron apps, they bundle Chrome with the application, and you open Chrome when you actually open one of these Electron desktop apps. Now, you get the Chrome DevTools with that. It's really great, right? But if you're talking to, and Chrome DevTools integrates with Node.js on the backend, so you can see everything. If you're talking to some Rust backend, that is system level, you can't use the browser DevTools with that. So they're building DevTools, and this is an event source system, more or less. And I'll show you why, and I'll explain to you what events mean in this context. So developer tools, you connect to an existing Rust application. Okay, so I'm going to go to my CLI, and I'm going to start my application. So in Rust, there's a tool called Cargo. It's like the NPM of Rust. And so we'll do this, and we start this application. So now I connect to it. And immediately, this is the console tab. Let me make this bigger for you. This is a console. And so if I do anything here, move the window, resize it, literally anything, you can kind of see the events happen in real time to show me what happened in my application. Okay, that's cool. But we can also see function calls. So I go here to call stack. And what you'll see is the cost of running functions through Rust on the operating system. So I'll click this button here to trigger some function, and you can actually see the function executing here in real time. I've made this function extremely slow just to illustrate the benefit. And so it took 7 seconds, but I can fire another one, and that took 300 milliseconds. And I can fire many of these in parallel, and you can kind of see the multi-threading with Rust here, right? And these are nothing more than events. And what you can also see is that some of them will get orange if they're kind of medium length and so on. But it gets even better with event sourcing. So I can click in this, and now I can see the entire time it took to go from request to response. And by request and response, we mean request from the browser to say, hey, Rust, can you do something? Rust to do some OS processing, and then to report back to the front end, okay? So you can actually see all of that happens here in order. You can also see the inputs to your argument. In this case, we request this URL, and you can see the output from the function. And all of this happens because of events. In fact, here, let me trigger another event. I click here, I trigger an event, and the system shows me state that is a response to those events, okay? Beautiful. You can also take a look at all the source code of your project, and this is just like, it's tremendous. But let's not spend too much time on that. I just wanted to show you an event-sourced system at play, okay? In the past, I've also worked at a company called G2I. This is like TopTel. Anyone use TopTel? It's a developer marketplace where companies go to them and say, hey, I need 18 engineers because I have this project, and they just have the right people for the right job, and they matchmake and they send them over. And as you can imagine, that is also a great use case for an event source system because it's just a big state machine. People apply to G2I, and then what? They need to be interviewed. They need to do a code challenge. They need to evaluate the code challenge. All of these are discrete states in a system. And when you transition from state to state, those are events. And then in the very end, they either approved for the team or rejected, right? So at G2I, I worked there in 2020, built an event source system that is in production to today and is probably one of the reasons for their success, okay? So with that, we've seen examples of 2 event source systems. What is an event source system? The best explanation I can give you for what an event source system is a system where there is no long-lived state that you can query. But instead, it's a system made up of discrete temporal events. That's events over time that you get a big fat list of events and you reduce on them. You just literally go event by event and you use it to derive the current state of the application. That is an event source system, okay? So if you think about it in terms of like a typical e-commerce website, Amazon.com/orders, right? Let's assume, I don't know the architecture of what they're doing there. It's probably something with COBOL from 1947. But I'm joking. But let's assume Amazon.com/orders is an event source system. And let's contrast that with Amazon.com/orders as a traditional, typical CRUD application. Okay? In a typical CRUD application, you go to /orders, and what happens? You send a request to the database, select columns from orders where user ID equals something. This is a very optimistic, bare bones illustration. You do a select, you retrieve the state, you present the state to the user. You can do this because the state exists in a database. Similar, if somebody made an order and they want to hide the order because they're ashamed of their purchase, like me, what they do then is they click hide order, and similar, you trigger some database query, update, order, where, ID this, set, hidden, true, right? So what you're doing is you're mutating state that is long-lived. Okay? That is a traditional system. An event source system, that whole state doesn't exist at all. Instead, you have an event store, and you just record events. Okay, so this user clicked buy, paid, made an order, order delivered, order, and then you get a list. You use all of these ordered events to compose the state of the orders page. You literally go look at all the events that said ordered, where the order is not deleted. So you get like 10,000 probably events or so, depending on how long you've been using Amazon. And like array.reduce, you just go order event by event by event. And at the output of that is the current state. That is an event source system. That is exactly what an event source system is. There's a number of questions that are probably coming up around the system, right? How does this even scale? We'll talk about all of that, okay? But for our intents and purposes, that is an event source system. You might be thinking, okay, but like why? Why does this matter? Why should we do this? And there's a number of reasons for it. As we just saw with developer tools, how else do you monitor the performance of expensive function calls? How do you monitor actions that happen in an application? Every time you console.log to debug your code, or use debugger statements if you want to be cool like that, those are all events. So event source systems give you a number of benefits that we'll talk about. For example, let's see, what you could time travel debug. How about that? In a system like Amazon.com/orders with traditional architecture, you can't really do that, right? You can't say, oh, I found a bug at this date on this time. Let's rewind the clock and go to the system at that state. You can't do that. With event sourcing, you can. Because again, you arrive at the current state by reducing over the past state. And you can slice that array of events such that you only go up to a certain point in time, inspect your system. Okay, looks good, doesn't look good, move forward. So time travel debugging is huge for business intelligence. Speaking of business intelligence, that's another thing, right? With an event source system, if you store just events, you get analytics and business intelligence for free. You have to do absolutely no other work. It's just there. Like, as a consequence, it's a side effect of your architecture. Anyone using in production Google Analytics, Fathom Analytics, some type of analytics tracker? Okay, yeah, like 3 of you. I would ask which one. I'm hoping it's the GDPR compliant one. But in any case, if you use an analytics system in concurrency or in parallel with a typical, CRUD style database system, you kind of have event sourcing already, but not really, because your state is not sourced from those events. Also, it's a bit worse for you because you don't really own the events. It's on someone else. Can you imagine the work they can do? They can look at everything that happens on your system, if they choose to, and derive a lot of insights from that, right? In fact, the business intelligence use case is so strong because this is exactly how, I'm quite sure, it's a theory, nobody will confirm, but Amazon, for example, will decide to make a vacuum cleaner. Did you know this? Amazon makes vacuum cleaners. Because through business intelligence insights, either through event sourcing or similar, what you end up doing is looking at, okay, who's buying? Okay, that's the cheapest one. I'm going to make one 20% cheaper and put it right next to that one on the product page, right? It's brilliant. You get all of this through event sourcing for free. Similarly, as your company grows and scales, you'll have to go through some type of compliance process for SOC 2 or ISO or HIPAA. Usually this is a thing. And as part of those audits, to get those certifications, you need to provide an audit trail. An audit trail is who did what on your platform, how often do they do that, et cetera, et cetera. If you don't have an event source system, the best thing you can do is give them like server logs, maybe an audit log from a database. With an event source system, you just get this for free. So the TLDR is, why should I care? Because you get a lot of benefits for free with a little bit of cost, okay? And we will talk about the cost. But this is why it's important. This is why people think there's room to invest in the space. Probably another reason, the original reason where it comes from, is event sourcing finds itself under an umbrella of something called DDD. That's domain-driven design. And this is actually a rule about how you structure your events. You can't just have events like read, write, update. They have to be specific to the domain your business is in. So like place order, remove from cart, etc. Okay? Those are some of the features of the event-sourced model. You get a ton of value for very, very little effort. Okay, let's talk about events. I hope by now I've given you some interest in like, okay, this is cool. Maybe we could benefit from this, right? He's nodding. Awesome. Thank you. His shirt is the blue screen of death. I love it. Best t-shirt at the conference. What are events? What makes up a good event? Well, we kind of started this discussion already because we mentioned DDD, domain-driven design. This is the golden rule of events. They are to be identified by domain language. Okay, so as I mentioned, no create, update, delete, that's nonsense. Go use REST. If you have an event, it has to be meaningful in your business domain. Okay, that's rule number 1. Rule number 2, events have to be self-contained. They are self-contained objects, meaning they don't need to borrow state or refer to state from some external source. They have to contain all the state. And then you might be thinking, okay, but this is going to get big. It doesn't matter. It's text. It's fairly okay. The idea is each event needs to be almost like a singleton. You should be able to have an event that you can replay in sequence and it produces appropriate state. You can also, by the way, see the value of event sourcing in the way of unit testing your application state. We'll talk about that with a live demo in just a minute. Events also are supposed to be processed by your event sourcing system in an idempotent way, right? What does that mean? That means if you receive 2 of exactly the same event, ideally you don't run them twice, or you don't deduplicate them. You have some way to identify them uniquely. You can imagine why this is a problem, right? If you receive a purchase event accidentally twice and it's the same event, then people will buy something twice, et cetera, et cetera. This is especially big of a problem at scale when you get into the distributed territory. We will talk about that if we have enough time today, okay? Let's think about some real-world examples of event-sourced applications. I showed you stuff, but this is stuff that you've never seen before. Those dev tools, for sure, you've never seen before because it's internal, maybe under NDA. I might get fired. But let's talk about some real-world examples of event-sourced systems today. How about, let's start maybe with the least accurate representation, and then we'll go more and more accurate, okay? In databases, there's a thing called a write-ahead log. Anyone know about the write-ahead log, the WAL? Okay, for database engineers. All of you are about to learn what a WAL is, W-A-L. Postgres has this. So when you do a write to your database, any write, this is DML, document manipulation language, so create, update, delete. What happens is Postgres will write this to literally a text file, a log, and only after it's committed to the log will actually go and modify the files on the disk. That's how it works. So this log is so close to event sourcing because it's literally every data manipulation that happens in your database. You can go look at it. Postgres will do checkpointing. So after a certain point of processing the log, it would be like, okay, I'm good up to here, and then it would just continue, okay? Is that event sourced? The answer is no, kind of. Because events are expected to be what? They're expected to be domain driven. And the write-ahead log in Postgres records update, delete, create. What does that have to do with your business? Absolutely nothing. Okay? So it's not event sourced. What else is not event sourced? There's a trend in the front-end world, I'm talking about this tomorrow, by the way, at noon, called signals. Signals, for those of you who don't know, is a stateful data structure such that when you read from it, you implicitly subscribe to its value, and then at any point when its value changes, you are notified by the event. Is that event sourced? Sort of. But you're not using the events to infer the state of an entire system. You're using the events to infer the state of like one value. So kind of, sort of. Most people in the front-end world prefer a library called React. Is React event sourced? Because you can like set state and that emits an event. Again, no, it's not. So then, okay, the question becomes, what is an event-sourced system? Redux, there's a JavaScript library called Redux that comes close. And there's also one event source system. I can guarantee you this. If you're an engineer in this room, there is an event source system that you use, that everybody uses always, constantly for your job. Any ideas? What is it? Yes. Git. Git is the gold standard, the perfect example of event sourcing that scales beautifully. You sometimes have conflicts, and this is actually a good thing, because when you implement an event source system, you need to prepare for those conflicts, but in your domain, right? Everything you can do with Git, you can do with event sourcing. And this should give you an understanding of why it's so special. Git is exactly the perfect example. And if you ever run into a question that you can't find an answer for by anybody, the perfect question for event-sourced architecture is what? Is what would Git do? WWGD. How does Git do it? Honestly, they have it absolutely figured out. We've been building software for decades on an event-sourced system that just works reliably every time. And Git is at major version 2 point something. Okay? For comparison, Angular is at major version 17 point something. And Git has been around for long. I don't know if they follow semantic versioning, but I thought that was interesting. Okay, so we have Git. We have Redux, we have a number of things. To illustrate, actually I'll save this for the end. I wanted to do a code example, but there's like 25 minutes left and there's so much content. We'll illustrate something at the end. Let's talk about scale. How do you scale an event-sourced system? How do you scale? Because as we talked about, right, if you derive the state from every event, what? How? Like I've been using Amazon.com for the past 8 years. Okay? On Amazon.com, I've done a lot of things. I made a lot of purchases. I've clicked a lot of it. There's been a few amount of events generated on that system. It's not an event source system. I just keep using it because we know it. I don't know what it is, but you can imagine in a typical application that's not event sourced, a user clicks on a thing and you update state. In an event sourced application, a user clicks on a thing, you emit an event, something else happens with that event. So 1 million database queries at scale is much less than 1 million events dispatched, and then more operations happening in cascade of that. Okay, so it does take a lot of resources. However, if we consider storage, is it expensive in terms of storage? In a typical event source system that I've seen in ones that I've implemented, a typical event is somewhere around 1 kilobyte. Okay? Not that much, not that little. If we talk about how expensive this is to store, the latest figures for cloud providers are that 1 gigabyte per month costs $0.0001 per month, per GB per month. The term for this in English is a mil. Not a million, that would be too, but a mil, M-I-L-L. That is 1,000th of a dollar, okay? You pay 1,000th of a dollar for 1 gigabyte per month. So $1,000 gives, wait, 1,000, you do the math, okay? Wait, I should do the math now. 1,000 gigabytes is $1, exactly, there you go. So 1 terabyte, $1, okay? That's a lot. And of course, this is not like storage you're going to access very quickly. This is long-term archive storage, which that's still, you could have tons of data. Assuming one event is a kilobyte, having that much is kind of nuts. So, okay, it's not very expensive for storage, especially if you're intelligent with archiving. How about then computation, right? I've been using, again, Amazon.com for the past, I don't work at Amazon, I should at this point. I actually don't want to. Can you imagine like peeing in a bottle because you're not allowed to go to, anyway, gosh. So, is it expensive computationally? I've been using Amazon. What's another e-commerce store? Can we like, eBay? Is eBay better? I've been using eBay. Okay, I've been using eBay for 8 years. Let's assume this is all pretend now. And in those 8 years, I've generated a number of events. And so, are you telling me that when I access my orders page, I go to orders, what it's going to do is like query the first event I ever go all those events over the past 8 years, and then like reduce over them, and then all of this on the server side, and then generate my page, and then send it over. Are you kidding? Is that how it works? That will never happen, right? That's kind of nuts to do all that computation ahead of time. So what can we do to fix this problem? And indeed, this is where we come to the point in our discussion where we ask, okay, but like what would Git do? WWG, how does Git do it? Does anyone know how Git manages? You've worked in code bases with probably millions of commits. How does Git intelligently, instantly take you to the right commit when you check one out? Okay. There's a technique in Git and in event sourcing, because Git is event sourcing, called snapshotting. And it's exactly what it sounds like. All of you are very smart engineers. I know you kind of get this. The gist of it is you derive a state from some stream of events, and you, at that point in time, take a snapshot of this, go like, okay, this is my state, store it in some type of snapshot store. Git stores it in your .git directory. You can actually go poke around if you want. And you store it in there, and then the next time somebody comes to read your state, you retrieve the latest snapshot. Ideally, there's some timestamp, last event ID. And then from the snapshot, you just replay all the subsequent events on top of the snapshot and then serve the state to users. So if I go to eBay/orders after 8 years, it's not going to get every event from the beginning of my account, but whatever the last snapshot was, plus any future events. Okay? And this way, you always minimize computations. But then the question becomes, okay, but like, how should I snapshot? When should I snapshot? Where should I snapshot? How does Git snapshot? Let's talk about that in some detail. We have 45 minutes. It's a deep dive, okay? Snapshotting can be done with a number of different criteria and a number of different techniques. I think in terms of application logic, it's not complicated, right? You take an event, you derive some state, you store it, but there's more questions here that we need to appreciate to understand the full engineering effort. Criteria number one, you can snapshot based on some type of event threshold. You can benchmark or reduce over events, and you can say, oh shoot, after like 10,000 events, our function starts to get slow. It takes too long, put it that way. You can you can guess the runtime complexity of your reduce function, and then you'll come at a number, it starts to slow down at this number, and then you can say, okay, every n events, every 1,000 events, store a snapshot, and that way you will always only process that number or less than that number when you derive the state, right? This is quite a standard practice. Most people do this, and it works. Criteria number two is time-based snapshotting. I think this is probably the worst approach. I'm just telling you about this for information, but I don't think anyone needs to use this, because it's just taking a snapshot of the state every 7 days, cool, or every some amount of time with the cron job or similar. The problem with this, of course, is events are not linearly distributed across time, right? Like I don't go make an order every day on Amazon. If I do, I have problems probably, but like I don't do this. I definitely don't update my profile picture on GitHub every day. So then why would you store a snapshot of my user profile? You know what I'm saying? It makes sense to snapshot the things with long history trails, probably with some type of time-based architecture, but typically you don't want to do this. Criteria number 3 is based on the available resources in your system. I really like this one. I truly think this is the superior way to snapshot. Most systems, even in Node.js, you can do this. That's saying something because it's so high level. You can get a read for available resources in the current VM or system. You could say, how much RAM do I have? How much disk space do I have? How much whatever? And then based on those, you decide, okay, it's time to snapshot and clean the house. Okay, and this I've actually seen some great success with this in terms of performance, because you can, in theory, using such a mechanism, keep everything in RAM. Literally all the events up to a certain threshold in random access memory. And random access memory, for those who aren't initiated, is the fastest way to store and access data in a computer, period. There's nothing better. No amount of like concurrency control with disk, none of that is going to even come close to random access memory. Random access memory is even faster than SSDs, solid state drives, right? Just by design, by hardware design. So what if we keep everything in memory? Is that possible? And the answer is yes. There's a website called, I think, doesitfitinram.net. Have you seen this website? This website is amazing because we'll do some, just does it fit in RAM? Does it run in RAM? Does it? Yeah, your data fits in ram.net. So okay, we have 5 GB of event. Let's make it 50 GB. This is one of those brilliant websites where you can just infinitely, you know. And what you'll see is the real upper limits of RAM in cloud-based environments are about there. 100,000 gigabytes, or let's get practical. I think it's about 64 terabytes. Yeah, 64 terabytes. That's kind of what I guessed. You can store, and of course, you need RAM for other things, so you can't store all your events in RAM. You can store a significant amount of events in RAM, serve them instantly, and you have, quote, like trademark, blazing fast software. Okay? And then when your RAM is somewhat low, and you know it's low because of events in your application logic, you just say, okay, send these to my archive store, priced at $0.0001 per GB per month, and then everybody's happy. That's one way. Another problem, or another term that goes with event sourcing is CQRS. CQRS. And what it means in plain English is you separate your reads from your writes. That's all. You separate reads from writes. It stands for Command Query Responsibility Segregation. A command is a write, a query is a read. You separate the responsibility. Okay? I've seen so many people like hide behind this word and go like, oh yeah, you don't know what CQRS means? Come on. So GraphQL as a specification has this built in. Literally, you query with the keyword query, you issue commands with the keyword mutation. That's GraphQL implements this. And this is often a topic that comes close to event-sourced architecture. And you might ask why? Why does that keep happening? And it keeps happening because event sourcing changes the bias of your system. What does that mean? Most systems today are read-heavy. Literally, how often do you scroll your timeline versus posting a post on social media? On X, formerly Twitter. How many of you hate me for using X? How often do you read LinkedIn versus post on LinkedIn? How often? Most things, by design of the way we use the internet, are read-heavy, okay? And when you introduce event sourcing, that read-heavy bias is somewhat challenged. Because why? Because every time something happens now, you're issuing a write. And so if your system is naturally read-heavy with traditional architecture, event sourcing will maybe shift it closer to write-heavy. And then you have to think about write-heavy considerations. What are read-heavy versus write-heavy considerations in system design? Read-heavy is I need my stuff fast, and I need my stuff consistently. In system design, there's a huge discussion topic on, okay, is this okay if it has eventual consistency? That means I get a response immediately, but it's maybe stale. Or does it have to be strongly consistent, meaning it's a bit slow, but it's always accurate? These are trade-offs with read-heavy applications. Banking applications, for example, will probably prioritize slow but correct, because it's important to know how much money you have, right? But for example, social media, how many likes do I have on my post? Could be 20, could be 23, who knows? Doesn't really matter, right? So read-heavy has these considerations. What about write-heavy systems? They have similar but different considerations, right? Because if it's, right, pun intended, because if it's write-heavy and you have globally distributed users, writes are happening all the time from many different people. So probably the biggest problem with write-heavy systems is if you have a Google Doc or a Notion document or something and you're collaboratively writing with another person, you'll see this happen. You'll see this happen, right? Like you'll have a word and you type more and they press backspace and you kind of fight with events. This is the problem with write-heavy systems. And with event sourcing, this problem is very real. You can have events accidentally written more than once because there's some network breakdown in your architecture and an event is maybe failed but not really, and then your system retries. That's very common. You could have events issued by two different people that cancel each other out. Like so much of this happens with event source systems, and this is why CQRS, or command query responsibility segregation, often goes with the event source discussion, because it does change the bias of your system, okay? How would you implement CQRS with an event source system? Ideally, you have some system to handle your event writes, some system to handle your reads, and they don't know about each other. The writes, ideally you use something that enforces and ensures consistency. Consistency is the name of the game. Can you imagine if you issue a delete event, or wait, let's think about this. If you issue an open event and then a delete event, but they're out of order and you delete something before you read it. This is very common, right? Especially in distributed systems. So you'd need something to manage your writes for you such that events arrive in order. Order is so important. So what do people typically use for this kind of thing? Anyone know? Huh? Version? Maybe, yeah, I haven't heard of that. The thing that I've seen used and that I've worked with quite a bit is Kafka. Kafka is an open source project from LinkedIn. How do you feel about that? LinkedIn innovates awesome technology. Surprising, right? Anyway, Kafka comes from LinkedIn because they had a use case where they had to process billions of events per day. And those events needed to arrive in order. And their biggest problem was throughput, because they wanted to take a bunch of events and feed them to machine learning models. And so they were like, how do we manage this throughput? So Kafka is an event system that ensures, most of the time, perfect ordering. Above and beyond that, it handles all of your writes for you, and it has durability built in, meaning you can store events in there for a long time. And it will store to disk, but it is probably the most efficient way to work with disk because of a number of optimizations it has. To give you an idea of how Kafka works, I want to show you a resource. I think it's Kafka visualized or something like this. I found it on the internet, and it's really cool. This one. It's from softwaremill.com. You can find this. It's just on the internet. And this is a great example of how Kafka works. So your system's producing messages or events, and in between the producer and the consumer, you've got some brokers. And what brokers do is they receive events and they think, okay, which consumer should I send it to? Send it. And they also enforce ordering. And how they enforce ordering is like, so what you'll see is the consumer saying, there, that thing just went there, right? So the consumer sends an offset to the broker saying, I'm good up to this point. And then the broker says, okay, I'm going to give you the next thing from that point. And it's a beautifully orchestrated system that scales extremely well. Let's scale this a little bit. So if we make the producer go nuts. So instead of 1 tick, it's 5 ticks. So now we're producing way faster. But we can also increase the number of brokers. So we have 4 brokers now. And you can see that we instantly get load balancing. Brokers are just your load balancers. Let's speed up the animation as well. And so, why is it stopped? How can this even stop? It's not even like stateful. I mean, it's not even like connected to a backend. It's so weird. Anyway, let's make this faster. And we'll scale the brokers to 5, right? And so you can kind of see, you get load. So when a producer produces things, look where the message goes. It goes to the freest broker. And so it's this intricate system that always ensures, now notice, there's so many different brokers, but the messages received here at the consumer level is always in order because it says, I have it up to 4, so send the thing from 4, receives the 5, sends the 5, okay, now 6. This is how it works. The cool thing is you can literally turn off a node. I'll turn off this node too. And the messages still arrive in order. It's an absolutely beautiful way to handle writes in a write-heavy system, okay? And so Kafka, CQRS, and event sourcing all go together for that reason. Kafka is extremely fast. Let me just check how many slides I have. for the sake of time, I don't want to bore you too much. Cool, yeah, we're good. Kafka is extremely fast for a number of reasons. We have a few minutes, and I'd like to talk to you about those reasons in depth. How do you make things fast? How do fast things work? I hope this is okay. I'm just having nerd fun here. Kafka, as its main data structure for event processing, uses a log. A log is a data structure, and it's specifically Kafka uses an append-only log. An append-only log. You might be thinking, okay, why is an append-only log fast? Is that the secret to Kafka's speed? It's multiple secrets to Kafka's speed. This is one of them. Because an append-only log is going to be fast in almost all types of hardware, especially hard disks, which is typically the slowest and worst form of storage. So Kafka will receive requests and then store events and retrieve events and all that from hard disks. And the reason it's so fast is because it's append-only, meaning you always write to and read from, ideally, an index that is very close to the end of the disk. Hard disks are slow because they need to literally physically spin when you query a file from them. You can query a file from literally any space on the disk. So if you're here and you need to go there, it will like spin. And that spinning is limited by physics, okay, like most computer science. So hard disks are slow, but Kafka using an append-only log is super fast because it's always just at the end. It doesn't have to traverse the disk space, okay? That's one really cool optimization with Kafka. Number two, it uses a mechanism called memory mapped files. How many of you are familiar with memory mapped files? Awesome, I love it. It's a way for the operating system to take a file from disk and like load it into memory and pretend the file is being read from memory. Again, heavily oversimplified for the basis of a discussion. You can talk more details after if you want, but my goal is everybody can understand this, okay? Operating systems have a thing called a kernel. A kernel is the host, is like the coordinator between hardware and software. Literally, it's like the thing that sits between you and the electricity. Okay? And it gives coordination to the hardware and gives you as much performance as it can. How it does this is by abstracting RAM. Any computer application that you use, if you have a machine with like 16 gigabytes of RAM, I can guarantee you that thing doesn't know anything about your physical RAM chip because there's an abstraction layer between the kernel and the software. Kafka has this abstraction. Every software has this abstraction. And so when you open up a piece of software, your kernel tells the thing, hey, listen, this is called RAM, and I have this much of it. But what it tells the software is RAM is not actually RAM, it's an abstraction on RAM. And the reason it does this is so it can optimize things. For example, everyone in this room, if we have a computer and it's not some supercomputer from space, we have more disk space than RAM, period. I've got a MacBook Pro with 16 gigabytes of RAM, 1 terabyte of space, okay? That's just how systems work. Because, again, you can't have that much RAM because RAM is expensive, because it's fast, et cetera. Supply, demand is economics, okay? So what the kernel will do is it will tell a process, something running on your processor, your CPU, I have this much RAM. That's the abstraction. But it lies depending on the needs of the application. If you're running something heavy, the kernel will be like, listen, I know I have 16 gigabytes of RAM, but to you, Adobe Photoshop, I have 32. Come on, let's go. And it can do this through memory map files, through literally saying, I'm going to extend RAM with disk. So when your RAM requirements go beyond the physical RAM requirements, I'm just going to proxy them to disk. You won't know. And that's memory map file. Kafka uses this extensively to make sure all writes and reads happen as if from memory, instantly. And that's another optimization it uses. Finally, there's another one. I'm really enjoying this. There's another optimization from Kafka called, what is it? I may be forgetting this. I have notes. Does anyone know? There's memory map files. There's, gosh. Okay, I'm just going to open my notes. You can all read my notes. I think it's important that you get this. By the way, I use notes with Obsidian. I don't know if you use Obsidian. Obsidian's a tremendous app. Look how deep my notes go. This isn't even the full presentation, but somewhere here, I have it. I have it. This is called an open source talk. Oh, zero copy, that's the one. Fantastic. I needed this for me, not for you. Zero copy is a way to run files without ever getting into user space. So I don't know if you're aware of this. Your computer is a multiverse, okay? There's the user dimension, and there's the kernel dimension, and they don't You don't mix them. Like your computer will not let you run stuff in kernel space for the most part, because that's the space where you could really do some damage. And because of that, there's a user dimension, a kernel dimension. Oftentimes when you request files, when you need to do something, there's copying that needs to happen. Copying from the kernel buffer to the user buffer, okay? The applications buffer, whatever you want to call it. And that copying can be expensive. Kafka uses a number of things, like in Linux you have a function called sendFile, syscall, to actually do stuff in the kernel dimension without ever having to copy it to multiple places. It can literally read and write to the network layer entirely in kernel space. Okay? That's some of the optimizations Kafka brings with it to help you with those things. And this is why CQRS is a thing with event sourcing. This whole time has been about event sourcing and CQRS. Separating your writes from your reads will help you, and that's how Kafka helps you do that. So then the question, okay, that's great. You've convinced me. Should I event source everywhere and I need to rebuild my blog. Should I go do that with event sourcing? And the answer is maybe. I think for practice, sure, great. So you can learn, you can reason, you can literally deploy. But then you have to think about it. You're using what? Kafka for a blog? It may be a little bit overkill, but I think it makes sense to evaluate systems. For example, do we care about business intelligence? Do we care about getting analytics for free? Do we care about time travel debugging? Do we care about chaos engineering? I didn't even talk about this, but with event sourcing, you can replay events up to a certain point in time, change like a few variables, and then replay all the other events on top of that, and you can literally create a branching timeline and see an alternate future, like you can with Git, right? And so you can do all these things. If that's important to you, and you can manage the complexity, then it's fine. If not, I wouldn't say it. Because like, here's the thing, in summary, there's a lot of complexity that goes with this. If you hire someone on your team and they naively open a pull request and they're updating something with a SQL query because you allow that, your infrastructure allows them to do that, that's going to be bad. And then you need to explain to them, no, we don't talk to that directly. We have to issue an event, and then the event. And before you know it, you're like this Charlie Day meme, you know, where he's got a pinboard and strings, and you're like, look, this is the event sourcing. And it's complex. And then you need to think about distributed systems. You need to think about reading and writing. You need to have item potency checks. You need to have all the... So if that complexity balances out well with the benefits of observability, business intelligence, replayability, time travel, all of that, then yes. So everything, probably not, but you just need to do some work. Ideally, I've given you the benefits, the trade-offs, enough to go run your functions and figure it out, okay? This has been 45 minutes. It didn't feel like it, feels more like 20, but I am launching a podcast. We do long lectures, an hour and a half or so, that you can find here. There will be a full-form version of this, along a bunch of other topics that goes extremely deep, and ideally, we always go to the CPU, because everything happens there, okay? I hate to do this, I feel really disgusting, but this slide was there and I forgot to remove it. I'm also writing a book on React. If you want it, it's there. Honestly, don't even buy it, it's not worth it. But hey, thank you so much. You've been a great audience. I really see you nodding and learning, so thank you for letting me be part of this conference. I appreciate you.
Thank you so much. What an enthusiasm, truly. Do we have any questions? We have like 2 or 3 minutes for a couple of questions. You have one. Let's go.
Hi, thank you for presentation, especially the slides. They were perfect.
Wow.
And I was wondering how many times have you presented this? Because
this is the first time ever.
Oh, so you're definitely very enthusiastic then. Yeah. Congratulations on that, and thank you.
That's the best question I ever got. What the? Amazing. Thank you, man. Anyone else have questions like that?
No. Okay, so what if I want to remove data from the event store because of GDPR or something?
Yes. This is an excellent question, especially because we work with append-only logs, right? That's fantastic. Thank you for asking. I was actually in the 1.5 hour thing, we probably talk about this. But similar to Git. Again, what would Git do? How would Git deal with it? With Git rebase -i head ~25, something like this. And you rebase all the past commits, and you literally rewrite history with Git. Unfortunately, that's the answer with event sourcing. You literally go back, you change a few variables, and then you commit the new tree of events. It's extremely error-prone, and ideally your system is architected from day one thinking about that. So when it happens, you're ready for it. But that is probably the worst thing that can happen to you with event sourcing. Because you can rewrite everything, you can derive the right state, but then you just never know, right, where the state will be. So that's how you would do it, exactly like Git, but you need to be extremely careful.